Hi, welcome students. In this module, we will understand and learn sets. Aditi was in her math class with her friend Priya. She whispered to Priya that she has just bought a set of summer clothes. The outwear collection includes a top, a scarf, a cap, and a pair of bellies. Their teacher overheard the conversation and asked them, "What is a set?" A set is a well-defined collection of objects. The objects that make up a set can be anything: numbers, people, letters of the alphabet, other sets, and so on. So, the collection of summer clothes Aditi mentioned in the earlier example forms a set. The objects of the set are known as the elements or members of a set. A collection is said to be well-defined if we can definitely decide whether a given object belongs to the collection or not. A set should satisfy the following properties. The members of the set should be distinct, not be repeated. The members of the set should be well-defined, well-explained. After going through this digital module, the students will be able to understand the meaning of a set, understand the notation of a set, understand the representation of a set, learn some special sets, understand and learn subsets and Venn diagram, understand operations on sets. Every object in a set is unique. The same object cannot be included in the set more than once. The following conventions are used with sets. Capital letters are used to denote sets. Lowercase letters are used to denote the elements of sets. Curly braces denote a list of elements in a set. Let's have a look at the examples of sets. The collection of all prime numbers less than 30. The collection of all vowels in English alphabets. The collection of even natural numbers less than 8. The collection of plants in a nursery. Use of symbols. If an element belongs to a set, then we use a Greek symbol epsilon, and if does not belong to a set, then we use the symbol epsilon cross. See this example. If A is a set of all prime numbers, then 2 belongs to A, 3 belongs to A, but 4 does not belong to A. Now let's see how we can represent a set. A set can be represented in two forms: roster or tabular form and set builder form. Look at this beautiful rainbow. It is a combination of 7 colors: violet, indigo, blue, green, yellow, orange and red. Let's denote these colors by V, I, B, G, Y, O and R respectively. So we can say that the rainbow is a set of these 7 colors. Let's denote this set by R. This form of representation of a set is called the roster form or tabular form. Roster or tabular form. The set can be defined by listing all the elements of the set, the elements being separated by commas and are enclosed within curly braces. Have a look at these examples. Remarks. In roster form, each element of the set must be listed exactly once. Repetition of elements is not allowed while writing the set. For example, the set of all vowels in the word cooperation consists of O, E, A, I. In roster form, the order in which the elements are listed is not important. For example, a set of A, B, C can be written in so many ways. However, in some instances, it may not be possible to list all the elements of a set. In such cases, we could define the set by another method called the set builder form. In this form, a set is described by stating a single common property of its elements. A variable followed by a colon is written to denote each element of the set. After the sign of colon, the characteristic property is written. Then enclose the whole description within braces. See this example of set C. This is read as C is the set of elements x such that x is an integer greater than -1. Let's discuss some special sets. The first one is the universal set. A universal set is a set of all the elements under consideration. It is denoted by U. For example, for the set of all integers, the universal set can be the set of all rational numbers. Have a look at these flowers. These are roses and orchids in the vases. If we create a set of flowers whose name starts with L, then it will be an empty set because there are no flower in the combination whose name starts with L. Empty set. The set containing no elements at all is called the null set or the empty set or the void set. It is denoted by phi or curly bracket. It may seem odd to define a set that contains no elements. However, one may be looking for solutions to a problem where it isn't clear whether or not such solutions even exist. If it turns out that there isn't a solution, then the set of solutions is empty. If a set U is of words in the English language, then words with more than 30 letters would be an empty set. Have a look at these flowers. You can see that there are 3 roses and 3 orchids. You can count these flowers, so they form a finite set. Finite set. Finite set is a set that has a finite number of members. If the elements of a finite set are listed one after the other, the process will eventually run out of the elements to list. The examples of a set of even numbers till 20 and a set containing x elements where x is an integer and ranges between 1 and 20. Look at the sky. Can you count the number of stars? No, because they are infinite in number. Infinite set. An infinite set is a set which is non-finite. It is not possible to explicitly list out all the elements of an infinite set. Some examples of infinite sets are of natural numbers and fractions. Look at these 2 vases. There are roses in one vase and orchids in the other. Now, when the 3 orchids are replaced by 3 roses, they become equal and form an equal set. Equality. 2 sets are said to be equal if and only if they have exactly the same elements. In this example, the first set of 1, 2, 3, the second set of 3, 2, 1, and the third set of 1, 1, 2, 3, 2, 2 are equal. In this second example, A is the set whose members are the first 5 positive whole numbers and B is a set of elements 4, 2, 5, 1 and 3. Now let's check if they are equal or not. They both contain 1, 2, 3, 4 and 5. We have checked every element of both sets. So, yes, they are equal. Note 2 more facts about equal sets. The order in which elements are listed does not matter. If an element is listed more than once, any repeat occurrences are ignored. Look at these plants and animals. Do they have anything in common? No. They form a disjoint set. Disjoint set. 2 sets are said to be disjoint if they have no elements in common. Let's see this example. If A is a set of even numbers and B is a set of 1, 3, 5 and 11, then A and B are disjoint. Subsets. If all the elements of a set A are also the elements of a set B, then we say that A is a subset of B, and we write the symbol stands for is a subset of or is contained in. Thus, A is a subset of B if an element of A is also an element of B. If A is not a subset of B, then we write, let's see an example. Let A be all multiples of 4 and B be all multiples of 2. Is A a subset of B? And is B a subset of A? Have a look at the solution. Here, both sets have an infinite number of elements. So first of all, we have to get an idea of what the elements look like in each and then compare them. Look at the two sets. By pairing of members of the two sets, we can see that every member of A is also a member of B, but every member of B is not a member of A. So, A is a subset of B, but B is not a subset of A. Intervals as subsets of R. Let A is less than B and B belongs to real number, then the first expression is an open interval including all the points between A and B. But A, B do not belong to this interval. This second expression is a closed interval which contains endpoints A and B and all the points between A and B. This expression is an open interval from A to B, including A but not B. This expression is an open interval from A to B, including B but not A. The set minus infinity plus infinity describes the set of real numbers R, and all the intervals described above are the subsets of R. Note, every set is a subset of itself. That is, for any set A is a subset of A. The empty set is a subset of any set A. That is, phi is a subset of A. For any two sets A and B, if A is a subset of B and B is a subset of A, then A is equal to B. Now let's see what a power set is. The power set of a set S is the set of all subsets of S, including S itself and the empty set. For example, the power set of the set 1, 2, 3 is a combination of different sets of 1, 2, 3 and also including an empty set. The power set of a set S is usually written as the power set of a finite set with n elements has 2 raised to the power n elements. For example, the power set of the set 1, 2, 3 is a combination of different sets of 1, 2, 3 and also including an empty set. This set contains 3 elements and so the power set contains 2 raised to the power 3 equal to 8 elements. The power set of an infinite, either countable or uncountable set is always uncountable. Venn diagram. A Venn diagram can be a useful way to illustrate the relationships between sets. In a Venn diagram, the universal set is represented by a rectangle. The points inside the rectangle represent the elements that are in the universal set, and the points outside represent the elements not in the universal set. Other sets are represented by loops, usually oval or circular in shape, drawn inside the rectangle. Again, the points inside a given loop represent the elements in the set it represents, and the points outside represent the elements not in the set. The sets A and B are disjoint because the loops don't overlap. A is a subset of B because the loop representing set A is entirely enclosed by loop B. Let's have a look at the example. Given the set A is the set of even numbers between 15 and 30, draw and label a Venn diagram to represent the set A and indicate all the elements of set A in the Venn diagram. See the solution. List out the elements of A. A is equal to 16, 18, 20, 22, 24, 26, 28. Notice that the set does not include 15 and 30. Draw a circle or oval. Label it A. Put the elements in A. Operations on sets. There are several fundamental operations for constructing new sets from given sets. The first operation is the union of sets. Two sets can be added together. The union of A and B, denoted by the symbol, is the set of all things that are members of either A or B. Look at the examples. The union of two sets, one of 1, 2, and the other of red, white. Similarly, look at the other two examples. The next operation is the intersection of sets. A new set can also be constructed by determining which members two sets have in common. The intersection of A and B, denoted by the symbol, is the set of all things that are members of both A and B. If A intersection B is an empty set, then A and B are said to be disjoint. Look at the examples. In the first example, the intersection of two sets, 1, 2 and red, white, is null as there is no element in common. Similarly, look at the other two examples. Properties of operations over union and intersection. The first is the commutative law. A intersection B is equal to B intersection A. A union B is equal to B union A. The second is the associative law. A intersection B within parenthesis B intersection C is equal to, in parenthesis, A intersection B intersection C. A union within parenthesis B union C is equal to, in parenthesis, A union B union C. The third is the law of null and union. A intersection phi is equal to phi. U intersection A is equal to A. A union phi is equal to A. U union A is equal to U. Idempotent law. A intersection A is equal to A. A union A is equal to A. Difference of sets. The difference of sets A and B written as A minus B is the set of all the elements of A which do not belong to B. For example, if a set A contains 1, 2, 3, 4 and another set B contains 2, 4, 6, 8, then the difference is a set containing 1 and 3. Complement of a set. If U is the universal set, then complement of a set A is the set of all elements of U which are not the elements of A. The complement of a set A is denoted by A dash or AC. In this example, if universal set is of natural numbers and another set A is of odd numbers, then A complement is a set of even numbers. There are certain properties of complement sets. Complement law. A union A complement is equal to U. A intersection A complement is equal to phi. De Morgan's law. A union B complement is equal to A complement intersection B complement. A intersection B complement is equal to A complement union B complement.
Law of double complementation.
The double complement of A is equal to A. Laws of empty set and universal set. Phi complement is equal to U. U complement is equal to phi. After going through this module, we have learned set. It is the collection of well-defined objects, roster or tabular form. In this form, all the elements of the set are listed and separated by commas within curly braces, set builder form. In this form, a variable is written to denote each element of the set, which is followed by the colon and the characteristic property, and then the whole description is enclosed within the braces. Empty set. A set is said to be empty set if it does not contain any element. It is also called null set or void set and is denoted by the symbol empty curly brackets. Equal sets. Two sets A and B are said to be equal if every element of A is also an element of B, and every element of B is also an element of A. Finite set. A set which is either empty or contains definite number of elements is called a finite set. Infinite set. A set which is not finite. It is not possible to explicitly list out all the elements of an infinite set. Subset. Suppose A and B are two sets, and if every element of set A is the element of set B, then A is said to be the subset of B. Power set. The collection or family of all subsets of a set A is called the power set of A, denoted by PA. Universal set. A set that contains all the elements of sets under consideration, that is, it is a superset of each of the given sets. Venn diagrams. Diagrammatic representation of sets is known as Venn diagram. These diagrams consist of rectangles and closed curves, usually circles, within the rectangle. The universal set is represented usually by a rectangle and its subsets by circles. Union of sets. The union of two sets A and B is the set which consists of all the elements of A and all the elements of B, the common elements being taken only once. Intersection of sets. The intersection of two sets A and B is the set of all those elements that belong to both A and B. Difference of sets. The difference of the sets A and B, written as A minus B, is the set of all those elements which belong to A but not to B. Complement of a set. Let U be the universal set and A is a subset of U. Then the complement of A is the set of all those elements of U which are not in A.